Hello, my name is Bradley Van Dam, and I will be doing exam for Chapter 30, and I'll be doing questions 10.1 through 10.4. So let's get started. So 10.1 gives us information, says the LC circuit in Figure 1 contains an inductor with 50 microhenries. The charge and current in this circuit oscillate with frequency of 445, and the maximum capacitor charge is 9 millicoulombs. So for this problem, we're just going to write down all the knowns, and I'm using M for units of henries. So we do 5, they gave us in micro, so 5 times 10 to the negative 5th henries. The frequency for 55 hertz, and the max charge, so Q max milli, so that's, negative third coulombs. Okay, so it's asking us to find the capacitance of the capacitor. So let's see, frequency Q max. Okay, let's use this equation here. So capacitance is equal to 1 over 4 pi squared times frequency squared times inductance. So we're looking for capacitance, and we have all of the following right here. So we just plug and chug. So we have 1 over 4 pi squared times frequency 455 hertz squared times inductance times 10 to the negative 5th henries. Let's plug all that in. Negative 5th. It gives us 0.0024. So let's do 1, 2, 3. So 2.45 times 10 to the negative third farads is the amount of capacitance we have. Negative 3 farads. So that is the capacitance of the capacitor for part A. And then part B says to find the max current in the circuit, so I max. So we can say, let's use I max equals 1 over MC times Q, and we can, so we can rewrite this to equal, instead of square root of MC, we can just say 2 pi times F times Q based off of the, for frequency based off the equation. So when we do plug all that in, so we get 2 pi 455 times our Q, so times 9 times 10 to the negative third. Let's plug that in. Then we get 25.7 as our, or in amps, as our max current in the circuit. So 0.7 amps is I max, and that's for part B. Okay, so that's 10.1. Let's go to 10.2. The LC circuit contains 90 microhenries, circuit contains 90 microhenry inductor and a 355 microfarad capacitor. So let's write that out for, so inductance M equals, that was in micro, so let's convert that, just basic Henry, so times 10 to the negative fifth, since it was 90 henries, and the capacitance 355 microfarads, 355, so that's 3.55 times 10 to the negative fourth farads. So it says at time 0, the capacitor has a max charge, so Q max of 0.4 microcoulomb or millicoulombs. So Q max, and again, we'll just convert that to from milli to regular. So let's say equals 0.4 milli. So that's times 10 to the negative third coulombs. Okay, so well, the question wants us to find the first time after t equals 0 when the capacitor has a charge, or when the capacitor charge is 0. So let me look at this real quick. Okay, so all right, let's use this QT Q max times cosine T. Okay, so we're looking for, so we're solving for time. So first time after time equals 0 when the capacitor charge is 0. So, okay, so, and we know omega is equal to MC. Okay, and so then we can convert this. Okay, yeah, and then we can do, omega t pi over 2. So this would allow us to solve for the actual time, but first we need to, solve for omega over here, so for radians per second. Okay, so we already have this info, so I'll just 1 over, okay, yeah, now it's just a matter of plugging and chugging. -5 times capacitance 3.55 times 10 to the negative fourth. And that should give us our answer in radians per second. So square let me do okay, so let's just round to the next whole number. So 5,595 radians per second is omega. 95, sorry. Radians per second. And now we can find the first time after time equals 0 that the capacitor charge is 0. So if we just we just move that over, so we get t equals pi over 2 times 5,595. So let's do that. Pi over 2. Doesn't look right. 2 wait, hold on. No, we're not multiplying, sorry. Okay, there we go, yeah. So that makes more sense. So 2.81 times 10 to the negative fourth seconds after time equals 0. Yes, I was going to say that does not make sense. So not multiplying, it is divided since we're moving it over. So then t, I'll just do equals 2.81 times 10 to the negative fourth seconds is the first time that the capacitor charge is 0 after time equals 0. So let's go to part D. Part D wants us to find the magnitude of the current in the circuit at this time. So I of t, okay, so we can just, yeah, it's negative dq of t over dt. And yeah, so we already know q of t is this expression here. So let's just rewrite that as q max and then omega sine of omega t. Okay, so yeah, but here we can observe that the sine of omega t, that's just going to be, I'll just do an arrow, that's going to equal 1. So it's essentially q max times omega times 1, or just q max times omega. So then we have, let's see here. So then we have the, let me draw a line so I can distinguish better. So yep, q max 0.4 times 10 to the negative third coulombs times omega, which we had just solved for right there as 5,599 or 95. So it gives us 2.4 is the magnitude of the current in the circuit at that time in amps. So that was part C and D. Let's go on to 10.3. All right, so three-parter. So it says the sum of the electrical and magnetic energies in the LC circuit is 0.8 joules. So we have U E. No, so it's just U. U 0.8 joules. At a certain instant, the energy is exactly half electrical and half magnetic. Okay, so that's divided by 2, essentially is what that sentence was saying. The capacitor charge is 5.3 millicoulombs, and then the current is 8 amps. So they want us to, for part E, find the capacitance. So let me write down the other stuff. So capacitance, oh, sorry, no, the charge of the capacitor. So Q is millicoulombs, so 5.3 times negative 10 to the negative 3, and current is just 8 amps. And it wants us to find the capacitance. Okay, so okay, so let's use this expression. So capacitance is what we're solving for. It's equal to charge squared times, and we'll do 2UE squared, but based off that sentence that we were given, it says electrical and magnetic energies in the LC circuit is 0.8 joules, but then it says at certain instant the energy is exactly half electrical and half magnetic. So this guy is going to be, again, we're just going to start plugging stuff in, and then divided by, ooh, that's not cool. That wasn't much better. 0.8 divided by 2, since it says half and half, squared. Yeah, so let's just plug that in. Two times 0.8 divided by 2. That gives us 1, 2, 3, 6 point. Oh, I forgot to square. I was about to say that doesn't look. I don't remember getting a similar answer to that. And squared. Still doesn't look right. 2 times 8, 2. Let me see if I do. No. Okay, so squared. Okay. We're going to begin with 3. Okay. Yeah, okay. 5, 1. Yep, okay. Farads, that is the capacitance. Okay. That was a slight slip up there. E, that's part E. Okay, and then part F wants us to find the inductance. So let's go over here. M equals, let's see. Okay, and then 2, now it's UM divided by our current squared. So again, 2, and then 8 squared, because the current is just 8, so that's just going to be 64. So 64 is the denominator. 2 times 0.8 divided by 2, and that gives us 0.0125, or 1.25 times 10 to the negative second. And that is in henries. EF. And for part G, it wants us to find the angular frequency of oscillation, so omega. So again, similar to the problem up here, we're going to use a similar equation. Omega equals 1 over inductance C, solving for omega. And since we now have capacitance and inductance, so we just plug and chug. So 3.51 negative fifth times, let's see. Oh, I just kind of wrote it backwards, but I'll just do, doesn't matter the order, 1.25 times 10 to the negative second. That is square rooted, all under 1. get 1509.7. Let's just do 15.10. Not 15.10, sorry, 1510. And that's radians per second, yep. Part G done. Last question, 10.4. I think this is a two-parter. Yeah, so it's H and I. Okay. So for 10.4, it is sorry, it is asking, or it's, first of all, let's just see what it's giving us. So LRC series circuit has inductance of 42 millihenries, capacitance C and R, or resistance R. Without the resistor, the angular frequency is 624 radians per second, but with the resistor, the angular frequency is only 208 radians per second. So it wants us to find, capacitance here. So solve for big C. Let's first write out what we're given from the problem. So angular frequency without the resistor, 624 radians per second, and then I'll just say omega 2, which is with the resistor, 208 radians per second, and and then we were given the inductance, so M equals, and they gave it in millihenries, so just keep it at 42, but then just times 10 to the negative third henries. And now we can solve for capacitance. So again, we can use the same expression right here, but we got to be careful of which ones, which omegas we're using. So in this case, we're gonna use omega subscript 1, so that would be 624. But first we need to actually structure it so that we can solve for C. So we got to rewrite this guy. Rewrite this as little swapping. So C equals, and then we're going to have 1 divided by inductance, and then omega 1 squared. All right, and so now we can start plugging in. So when we have the 42 times 10 to the negative third times omega 1, 624 squared, all over 1. So let's see what that gives us. Squared. Okay, 6.1147 ... So let's cut it off at 3 sig figs. So 6.11 times 10 to the negative fifth, and since we're solving for capacitance, that's in farads. So and that is H. And the last question wants us to find the value of R, so for resistance. So now we're going to use our omega 2 since it's asking for the resistance. So since omega 2 was using resistance, we're now going to actually solve for how strong that resistance value is. So we're going to say omega 2. So essentially we're just incorporating the incorporating the resistance in this case. So now we're going to do, instead of 1 over square root of MC, we're going to do square root of 1 over inductance capacitance minus the resistance squared, which is what we're looking for, just the resistance, divided by 4 times inductance squared. So we're going to have to do some moving around again to actually solve for R. So let's see what we can do. So first we can just get rid of the square root. Square both sides. Still solving for R. And now from here, we'll just do a little mental swapping around. Okay, yep. So we know everything else on the other side of the expression for solving for R is going to be square rooted because that's squared right there. So square root, and we're going to have square root of 4m, 4 times inductance, over, that doesn't really look that good, divided by capacitance minus 4 times inductance squared, and then times omega 2 squared. So if we plug everything in, so I'll just write it down here, again, still R. So square root, so M42 times 10 to the negative third over capacitance, which we just solved for, 6.11 times 10 to the negative fifth minus 4 times third, and that is squared times omega 2, which is 208, that was given, squared, and this is all square rooted as well. So let's plug this expression in. Let's see what we get. Square root 4 times yada yada minus 4 times 42. And this is squared, and then 208 multiplied by that is also squared as well. And then we get 49.44 and then a bunch of garbage values. So let's just say 49.4. So our resistance is of the resistor is 49.4 ohms. Part I. Okay, so that wraps up chapter 30, exam 30.